Welcome to the 2025 Grubb Parsons lecture. The lecture itself denotes the history of a very famous Northeast engineering and optics company, Grubb Parsons, that was founded exactly 100 years ago this year, that built most of the best optical telescopes and infrared telescopes still in use today around the world. The sign of a good telescope is to see the word Grubb Parsons written on the side of it. I have used many of them over the years, and I am sure many of you, if you go off into professional astronomy, will be using them as well in many years to come. I should also add that this lecture series is sponsored and funded by the Royal Astronomical Society, a very august and very important organisation, and I encourage you as students to make use of the very generous low fee for joining. I have been a member for well over 30 years, and I get value for money for it every year. So please, if you are interested in joining the Royal Astronomical Society, find me afterwards or at some point during the next few weeks, and I will give you the information required. But first, let us pass over to Paula Chadwick, Head of Department, who will now introduce the speaker.
Thanks, Alistair. So it's a great pleasure to welcome you to the Grubb Parsons Lecture for 2025, and also to welcome our speaker tonight. I'm going to just start with a little bit more history of Grubb Parsons, which Alistair's already mentioned. As he said, it was a telescope manufacturing company of great renown. And the Grubb part was Thomas Grubb, who started a company in Dublin in 1833, actually making billiard tables, of all things. He then diversified into making telescopes, which became very well known for their excellent optics and superb clock drives. Among the many telescopes that he built around the world, he helped to build the telescope at Burgh Castle for William Parsons, which, as we know, played a really important part in our understanding of the universe. Grubb's son, Howard, took over the company in 1864, and he enhanced the company's reputation even further, and particularly with equatorially mounted telescopes. He also invented the reflex sight, which is the heart of heads-up displays even today. After the First World War, the company started to struggle financially, and it was bought 100 years ago, as Alistair said, in 1925 by Sir Charles Parsons, who was inventor of the steam turbine and the youngest son of William Parsons of the Burgh Castle telescope. Now, the Grubb Parsons works were based at Heaton in Newcastle, and as Alistair said, they were very, very important. They built over 50 major telescopes around the world, including the Anglo-Australian telescope, the UK infrared telescope, and the William Herschel telescope. William Herschel telescope was the last big telescope that they built before the company folded in 1985. Now, today's speaker is also a pioneer in telescope building, but I think it's fair to say that Grubb and Parsons would have great difficulty recognizing it as a telescope. He has a very long-standing connection with the physics department from the 1980s right up until now. One result of this connection was a textbook written with Alan Martin, who's sitting over there, called Quarks and Leptons. I looked this up on Amazon, and it now sells for just shy of £150 for a paperback copy. So this may explain why the copy that used to be in the James Knott room in the department has now disappeared. Also in the 1980s, our speaker started his long association with neutrino physics and astrophysics, first of all with the Amanda experiment. As Vilas Research Professor and Gregory Bright Professor at the University of Wisconsin-Madison in the USA, he is now the Principal Investigator of IceCube, a kilometre-scale neutrino observatory at the South Pole. Like the telescope at Burgh Castle, IceCube is also transforming our understanding of the universe, and I'm sure we're all excited to hear about the latest results. So please welcome Professor Francis Halzen.
Thank you, Paula, for this introduction. I I think I came the first time to Durham in 1971, and I have never held a job here, but if I integrate the time I spent here, it must be years, and I enjoyed every minute of it. So it's a pleasure to be back here and to tell you my story about building a neutrino telescope. It's a strange story, and so I have the menu for you here, and so we'll have to go through a long list of concepts. I know most of you know what a neutrino is, but I'm going to reintroduce it in the context of neutrino astronomy. And then I will tell you about the telescope we built and what we actually ended up seeing in the last few years. So what's a neutrino? Now, remember from your high school physics, the world is made of protons, neutrons, and electrons. And protons and neutrons make nuclei, then you put electrons around it, and you have atoms. Well, this story is very incomplete, because in the 1930s in Cambridge, people started to do experiments with neutrons that had just been discovered and decayed. And a neutron transformed into a proton and an electron, positron actually, and an electron. And so if I'm the neutron and the proton goes this way, the electron has to go that way. And they saw this was not happening. They went in the same direction occasionally. And so Pauli suggested that what's actually happening is that a third particle was produced, which he called originally the neutron, but we call now the neutrino, and that this particle escaped and carried off the momentum. You know, when two particles, you have the decay and two particles go in one direction to conserve momentum, something has to go off the other way. And he proposed it was a particle. Obviously, the apparatus didn't see this particle. And so that was the origin already of this being called the ghost particle. And these measurements, well, I have to go here. These measurements by Ellis and Mott, they actually reconstructed the direction, and they even measured that the particle had no mass, or a very small mass. And so this, by today's standards, is what we call a missing mass experiment. And that's how you detect particles. It's a standard technique in Geneva, at CERN, and everywhere else in the world. But they couldn't imagine that they had discovered a new particle, so it had to be rediscovered in 1956 by Reines. So the story is incomplete in the sense you have to add a neutrino to this list. And in fact, the neutrino is more common in the universe. There are more neutrinos than any of the other three particles. And how do you think of this particle? I just told you by the decay of a neutron it becomes a proton. Changing neutrons into protons is called nuclear physics these days. And so the neutrino is actually, you can think of it as the agent that makes nuclear physics possible. So without a neutrino there is no nuclear physics. And then you can go through the list on if there were, without nuclear physics, there are many reasons why we wouldn't be here. There would be no Big Bang. Stars couldn't explode without neutrinos, so the material that we are made out of in this room that comes from the explosion of stars wouldn't be around. The sun wouldn't shine. The sun is a nuclear reactor. At Fermilab in Chicago, they produce neutrinos, and I'll come back to that at the end of the lecture. They produce neutrinos, and now I have to introduce my energy units of 1 gigavolt. The neutrinos I will be talking about today have typically 100,000 to 1 million times that energy. but there's still a connection, as you will see. You emit neutrinos from the salt decaying in your body. And then this is very important, the top right picture. That's a reactor, and you see it's covered with water to prevent the radiation from escaping or doing damage. And you notice that water is blue. And so it has something to do with the particles that come out of the reactor, turn this water blue. This is actually the mechanism we are going to use to detect neutrinos eventually. The Earth emits neutrinos, but here is an important part of the story. Cosmic rays, mostly protons, I will confuse cosmic rays with protons. So cosmic rays, when they hit the atmosphere, they make neutrinos. And so they make neutrinos through the mechanism as shown there. I'll come back to this. But the result of it is that in these collisions, neutrinos and muons are produced. Muon is the last particle I will introduce, so don't panic. It's not a typical particle physics talk. You know all the particles in the play by now. And so if you look up at the atmosphere emits neutrinos and muons. And so this is a problem, because next we are going to try to do astronomy with neutrinos. But you look up at the sky, the atmosphere emits neutrinos. So it's like you have a cloudy sky, but the clouds never go away. And that's one immediate problem for introducing the concept of neutrino astronomy. So what's neutrino astronomy finally? Well, what's astronomy? I'm a physicist, so I don't know much astronomy, but so I want to introduce this picture. That's the sky you don't see really when you go out at night. But if you were in a place where you could still look through the clouds, then you would see the Milky Way. And so this ellipse is a way to project the whole universe onto a piece of paper or a piece of on a screen. And so the major axis of the ellipse is our own galaxy. And so you see the Milky Way. Then what has been a very successful enterprise in astronomy is to change the wavelength of the light, or in physics terms, the energy of the photons, of the particles of light. You know, this is quantum mechanics. So you can, I mean, as a particle physicist, I know this as 1 electron volt, but as an astronomer is a 10 to the minus 6 meter wavelength. And so if you turn the wavelength towards the red, eventually you see this sky, and that's the microwave background, 411 photons per cubic centimeter. And it's totally different. So by changing the color of the light, you learn totally new things. So what if you, instead of going to the red, you go towards the blue, then the sky looks this way. And these are high energy photons. By now the energy is 1 GeV, like the neutrinos at Fermilab, and the wavelength is 10 to the minus 15 meters. And so you can go both ways, in both directions. Eventually you run in trouble. I'm going to talk how you run in trouble, about how you're in trouble when you go more towards the blue. If I keep cranking down this wavelength, this is what you see, nothing. The sky turns dark. And so there is this sky out there that we have never seen before. It's like the dark side of the moon, right? And so here is the more professional way to look at this. This is now, instead of in pictures, this amount of energy that we capture coming from the universe to our telescopes. And you see this peak here, that's the microwave background, it dominates the sky. These are radio waves. This is infrared light, visible light, ultraviolet, X-rays. And here you see the gamma rays in my last picture. It's a picture taken of gamma rays reaching the sky from a telescope and on a satellite called Fermi. And you see they measure and go to smaller and smaller wavelength, and whoops, you see the sky turn dark. Why does this happen? And of course you can already anticipate the rest of the story. We are going to try to look into that dark universe with neutrinos. The concept, by the way, of doing this, all the fundamental papers were written by 1960. And from 1960 on, it was a battle to find the technology to do this. So a gamma ray is emitted far away at some galaxy or whatever. It travels through the Earth, but it's eventually going to meet one of these 411 microwave photons, making it plus or minus pair, and then the astronomy is finished. Because once you have charged particles, you don't have astronomy. Charged particles are bent in the magnetic fields in the universe, which we don't know very well. But there are magnetic fields in the Earth, and so before they reach our telescope, they will be bent in the magnetic field of the Earth. And so that's why we know cosmic ray protons fill the universe for more than 100 years, and we have no idea really where they come from or how they are accelerated. Is because protons are charged particles, and they lose their direction. So that's the reason, the basic reason why the sky turns dark. Now, neutrinos don't have that problem. Neutrinos don't interact with anything. They are not bent by magnetic field. They have no charge. They have no mass. I know they have a small mass, but in this talk, this doesn't matter. It's irrelevant. And so they are exactly like photons, except they don't interact. Don't interact with the microwave background or anything else. So the idea of neutrino astronomy is that you will still see this galaxy in this dark universe if you use neutrinos. So is there anything out there? I had to face this question actually. When we proposed to build a neutrino telescope, people said, "How do you know there's something interesting out there?" Well, we know there is something interesting out there. There are these cosmic rays. And some of them, I remember very well, 1991, how a modest experiment in Utah identified a cosmic ray that had 300 million TeV energy. A TeV, by the way, is 1,000 GeV, and so the Large Hadron Collider in Geneva is 14 TeV. So this particle has been accelerated somewhere to 300 million TeV. And so if you use the magnets of the Geneva accelerator and you fill the orbit of Mercury, you could accelerate that particle. And I think we have found out that's not the way nature does it. So how do you build a square kilometer neutrino mirror? Why a square kilometer? Of course, I said all the fundamental papers were written by 1960, and but the theorists, in their wisdom, began to estimate how big a detector, a telescope you needed to actually identify neutrinos from objects in the sky. And by 1969, the first paper started appearing with the idea that you needed a kilometer square detector, which means that you build a kilometer cube neutrino detector. You don't detect neutrinos with a mirror. And so that actually stuck, this number, and it actually happened to be true, as we will see. How do you detect neutrinos? It's easy. You need light sensors. For a physicist, we call this photomultiplier tubes, and water. This is the Super Kamiokande detector in Japanese Alps. The problem is a kilometer cube neutrino detector is 10,000 times bigger than this. So you need a better idea. And that idea also goes back to 1960. This man, Moshe Markov, suggested, and rather than reading what he said in his talk at a Rochester meeting in Syracuse, I'll give you the cartoon. So you need light sensors. These are basketball-sized light sensors. So light comes in and they transform the light into an electric signal. And so then his idea was you take lots of them, you take a kilometer cube volume of water deep in the ocean where it's dark and you have very clear water, and then you wait for a neutrino to come through the Earth. What does it do? It goes through your detector. But 1 in a million will hit a nucleus in the water, and then it will make a small nuclear reaction. The neutrino disappears, the nuclear reaction produces particles and turns the water blue, just like the reactor you saw in my previous slide. And among these particles, if there is a muon, this muon at the energies we are working travels for kilometers through the water. So it travels through your detector, you can detect it. But notice, what's special about this is look at the shape of the light it emits. These muons go at the speed of light in vacuum practically, 300,000 kilometers per second. But the light in water travels at 3/4 of the speed of light. So it's like a boat that goes faster than the waves it produces, and then it produces this shock wave, this bow wave. And if you measure the shape of the bow wave, you know that the direction of the muon, which is totally aligned with the direction of the neutrino. So you have a telescope. You not only detect the neutrino, you know its direction. So that was the concept introduced by Markov. Here you see a big step many, many years later. Here you see a picture of a muon going through a detector. If you look very carefully, you see dots on these vertical lines. Each of these dots is one of these 10-inch light sensors. And then you see how they capture the light emitted by the muon when it travels through the detector. By eye, you can reconstruct to a few degrees where this neutrino came from, or this muon, and we can do this now to 0.3 degrees or better at high energy. Not much better, however. It's not a great angular resolution for an astronomy. So if you didn't get it, this is the movie with the speed of light slowed down. And you see the color. Red tells you follow the rainbow, the direction, and the size tells you this is our online display of the detector. The size tells you how many photons were detected by each sensor. So those photomultipliers you were looking at, they are actually not in water, they are in ice. And so in the late 80s, we began to develop the idea at the University of Wisconsin in Madison that it was simpler to freeze photomultipliers in ice at the geographic South Pole than put them in water. And history has proven us right. This is totally counterintuitive, but we had thought this through and thought this is the way to do it. And, the water detectors are just appearing now on the scene, but we have been taking data for more than 10 years because it did turn out to be simpler. This is the geographic South Pole. The first piece of luck we had was that there happens to be a station a scientific station of the National Science Foundation, which can support experiments of the type we want to build. Everything goes into the South Pole by plane. You see the runway. And this is the IceCube project during construction. So all the equipment is built in Madison, Wisconsin. It goes by boat or by plane to Christchurch. From Christchurch, New Zealand, where we have a logistics center at the airport, it goes to McMurdo on the coast of Antarctica, and then it's another 9-hour flight from McMurdo to the South Pole. So this chain eventually gets your equipment there and gets people there. When you arrive at the South Pole, that's the South Pole. It's a desert. And it's the weather is totally stable. It fluctuates on days, but every year it's a desert. You get the same weather. And we made this discovery that you stand there on 3 kilometers of really pure ice, pure and transparent ice. I'll come back to this. There is this station, and this station is open during the 6 months of summer and during the 6 months of winter. So you can keep people there for the whole winter and operate the detector year-round. So you think every big science project starts with grandiose proposals, and these are the first photomultipliers that were put in the ice at the South Pole. And the way this was my lab, I am a theorist, I didn't have a lab, so I had a place where our group had a table tennis table, and we removed it and put photomultipliers in pressure vessels. Then I hired someone who was an expert in hot water drilling, but that meant someone who drilled cores this big in glaciers. And so we just told him we need something bigger than that, and he started working on it. So by the early 90s, we were putting photomultipliers down at depth in the ice. And so by 2000, we actually had built a small detector here. You can see it. It contained 650 something 8-inch photomultipliers at 800 meters. That's the geographic South Pole here on the right. And we made a big discovery. It had nothing to do with neutrinos. We found that at depths below 1.5 kilometers, we didn't know exactly where at that time, that blue light absorption length was 270 meters in the ice in the South Pole Glacier. In fact, at that time you couldn't build a substance in the lab that was as transparent as this ice. And we now know that the reason is that this was snow. Well, we knew then it's snow that was frozen 50,000 years. It fell on Antarctica 50,000 years ago, give or take a few thousand years. And then that snow was so pure that it translated in this incredible absorption length. And of course, you can immediately guess, if the light travels that far, I don't need nearby photomultipliers to detect it. I can spread them out and fill a kilometer cube. And so this experiment was called Amanda, and you see our logo we stole from The Economist. And soon enough, like 10 years later, we discovered neutrinos. And you've already seen a neutrino in IceCube. This is a neutrino in Amanda. And so what do you do at this time? This detector was like 20 times too small. And of course, it didn't see anything. It didn't do astronomy. But then there is a procedure. By the way, I make this look easy, but this is not me. It was quite an adventure, actually. But what I worried about is you splash this story in Nature, make outrageous claims of how great the science is going to be when we build a kilometer cube detector. And we were helped by being declared instantly one of the wonders of astronomy with the Hubble telescope. But you see, we were in a category by ourselves as the weirdest telescope. This is Scientific American, but we took all the publicity we could get and proposed to build a kilometer cube detector. This became an industrial enterprise, and typical of particle physicists, you know, Amanda was a photomultiplier with a cable that traveled 1.5 kilometers to the surface, and then we tried to reconstruct the electric signal from the light. This was quite, but now of course you see we transform the light signals into electric signals, and the electric signals, you know, by digitizing, you see here the digitization electronics, and so off we were. And so IceCube is you know, still, you saw a picture, you saw a neutrino from it before, a kilometer cube detector with 5,160 10-inch photomultipliers, so about the size of a basketball. And if you could go inside the detector, you would see these kilometer-long strings with a cable attached to a cable. Every 17 meters there's one of these light sensors. If you go 125 meters away, like from here to the physics building, you see another string, and 86 of these strings fill a kilometer cube. That's the concept. I can actually show you a picture of this detector. A few months ago, a plane flew over the South Pole with ground-penetrating radar. And so this is a picture. If you start at the top, I cannot see my, if you start at, the black part is the sky, then you see the surface at where the South Pole is. Then you go 1.5 kilometers deep and you see the outline of the detector from the radar picture. And if you go another 500 meters, that line is the bedrock on which the 3-kilometer ice shelf is, that supports the 3-kilometer ice shelf. If you look carefully in the top left of IceCube, you see the Amanda detector, which is still there. We built IceCube around it. So now I'm going to avoid all questions at the end of how you put photomultipliers in ice. I'm going to tell you this first, and then we'll go to the physics. What you need is a 4.8 megawatt power plant, and it's like 40 car wash heaters. That's all it is. Then you deliver hot water under pressure, boiling water. Water boils at 3-kilometer height, 90 degrees C, and you deliver it under pressure. And so I'll show you the movie of what happens. So this is the hot water drill tower, and the top 90 meters is snow, so you just melt it with a heating element. And then this hot water drill comes in, and you see it's a nozzle that puts out this water under pressure, and it falls by gravity. And 2 days later, you have transformed, there are no holes. 2 days later, you have transformed ice into water. And it's about over a distance like this, in which you can lower the instrumentation. Oops, what happened to my movie? Oh, okay. Yeah. So, how is this done? It's like a circus train of equipment, except it's on sleds. And so this is the drill tower. And next you will see that's a 2.5 kilometer long hose, about that thick, through which this water will eventually go 2.5 kilometers. These are the buildings that contain the car wash heaters. These are the generators. This is normal fuel, runs these generators and produces the power. And you see, this is the moment the drill comes out. This is 2 days later. And so you have a column of water. Ice is an isolator. So that water stays liquid for, 30 hours or so. That's how we prepare it. And then the whole circus train moves up 125 meters further. So here are the light sensors in their pressure vessels ready to go, and you actually build the detector as you deploy it, as you will see here. So this is the cable that goes down, bringing the voltage, the power to the sensors, the digitized signals of light that are detected come up through the same cable. So that's so you do this 86 times, and you have a kilometer cube detector. And so this is a picture in. This happens typically over 2 months in Antarctic summer. And so you see 20 cables coming out of holes, and they go into this 2-story building, and this 2-story building is just a computer center. And so there is no IceCube actually. Each of these photomultipliers act as an independent experiment. Whenever they detect light, they digitize it, send it to the computer. The computer collects all these signals and put them together in neutrino events, one of which you saw some time ago. So what happens when you turn on this detector? You detect muons. The computers reconstruct muons. And here you will see how, it doesn't run. Let me see if I can. That's a pity. No. What do you see? I was going to show you the detector reconstructing muons 3,000 every second. And that's the flux I was talking about of muons and neutrinos produced in the atmosphere. So the bottom line is you run this detector for a year and you have 100 billion muons made by cosmic rays. You have 100,000 atmospheric neutrinos. They are actually interesting for physics I won't talk about today, but they are a background for the physics I do talk about today, that is muons coming from the cosmos. Now you cannot tell a neutrino is a neutrino. Nothing tells you whether it comes from the atmosphere or the cosmos. And so that's something you have to try to figure out. But so typically this, we see a neutrino every 5 minutes. And we see muons at a rate of 3,000 per second. And so the main goal is to collect all these, make sure they are neutrinos and cosmic ray muons, and throw them away and hope there's something left that comes from the universe. That's the concept. So we built this detector, and I remember this comes from not Scientific American this time, but from New Scientist, a respectable magazine. And I got this depressing news that our chance of discovering cosmic neutrinos was 1 in 6. And the chance that you would detect the Higgs boson in Geneva was also 1 in 6. And the chance of discovering gravitational waves was 1 in 500. And you could bet on this page. It was eventually taken down. But I remember being very depressed when I saw this. I thought we had a better chance than that, and we did. So we ran this detector for 2 years, and New Scientist was still right. We didn't see anything. And we were looking for some science that I won't introduce. It was very interesting. Even a theorist could analyze the data. And while we were doing this, we found by accident this event. Where is the muon track? There is no muon track. This is an electron neutrino making an electron, not a muon neutrino making a muon. And an electron neutrino will make a high energy electron, and that electron will make an electromagnetic shower that will go about the length of this blackboard, this whiteboard. And in a kilometer cube detector, a shower the size of this board is a point source of light, and that's what you see in this movie. But you see, this thing is isolated. It's a neutrino. Nothing came in. The only particle that can have made this, that escapes all detection and then makes this electron is a neutrino. And this was a known technique. It's called contained events. And Super Kamiokande, I showed a picture of, had already invented this technique to look for neutrinos. And in fact, we saw 2 of them, and then it was not a brilliant idea. Let's go back to our first 2 years of data and see if we can find more of these events. And in fact, here is to reset the scale of what you are looking at. This is this event superimposed on the data center, which is on the campus in Madison, Wisconsin. This is the lake, and you see, we can tell these events, as it said before, something like 300,000 photons in it. And we know where each one is to only about 2 nanoseconds, which is that much. But these events go 6 city blocks. And so that's good enough to reconstruct its energy, its direction, not as well as a muon track, but we know it's a neutrino. There's no doubt about it. In fact, these events have so much energy that they are very unlikely to be produced in the atmosphere. So we immediately went through the 2 years of data, and it looked easy. By then we found 26 more events and published. So you can look at all of them here. And a few days, literally 2 weeks, I think, after we finally had the courage to publish this, of course in Science magazine, because eventually we want more money again, right? We were declared the breakthrough of the year by Physics World. And I remember this was some of the worst experience in my life. The whole time of the press conference, I was thinking, by then I could answer any question without thinking on this topic. I was thinking, how are we going to walk this back if it's not true? And I didn't sleep well, probably for a couple of years. So what did we see? And in fact, we saw these neutrinos coming from all over the sky. It looked just like cosmic rays, which didn't tell us where they came from. And but there were 2 surprises. Yeah, now neutrinos, even for us, it was some boutique science. It was not real astronomy. We were looking for something special. Well, we were not. Remember, this is the light in the universe that turns dark. The energy we detected in these neutrinos was actually much larger than the amount of light in the universe. So this dark universe is actually dominated by neutrinos. They are not boutique science. They dominate the science in this extreme universe. That was the first surprise. The second surprise was the following. So after some time we had, this is a map with 166 contained neutrino events. So there's no background. These are all neutrinos, and you see, you can compare it with the gamma ray sky and with the Milky Way, and look what's missing. There is no Milky Way. And in fact, nobody took the hint of this until much later. Now it's amazing that nobody thought of this, but it's simple geometry that if there are sources coming from the sky, you see the sources in your own galaxy first. That's why you see in all these maps you see the Milky Way. If you don't see it, that means that elsewhere outside our galaxy, there are sources of neutrinos that don't exist in our own galaxy. And if anyone had thought about that, the obvious idea is what's missing in our own galaxy. We have a black hole like every other galaxy, but it's not active. So the answer is probably, you cannot prove this, but it's a guess that it's something to do with black holes, right? In active black holes in other galaxies. So, but nobody made this connection until it was too late. Okay, I think I said all that. So we already started getting really interesting information, even though we didn't see any sources. So what about sources? That's not as easy as it looks. I told you proudly, we see under 38,000 in this case, neutrinos per year. So this is the first year of data. And so these are the neutrinos, and you see where they come from. And you see there is no galactic plane, and it's a totally uniform sky. And we know now from measuring the flux and knowing the acceptance of our instrument, we know that in this map there are 200 cosmic neutrinos among the 138,000. So we had to go and find them. So here is a 4 by 4 degree. So this is a tiny fraction of this map. And here you see a source. You see the red dots? Those are neutrinos coming from a source. This is actually simulation from our simulation of the detector. But it's a source that we would recognize in our data. But look on the right, if I don't color these events, you see nothing. And we developed a technique where we can not only pick out these events, but we can calculate the probability that it's a real or a false signal, which is very important. And I won't go through this, but the idea is simple. What this map does is it looks at every point in the sky and asks the question, is there a cluster of neutrinos that have on average higher energy than the ones that come from the atmosphere? And so after 10 years of data, we saw nothing. So what do? You build a better detector. And I make this part short, but by then we understood the optics of the ice better. We began to calibrate every photomultiplier. The experts in the audience will recognize this picture. This is the 1 photon signal in a 10-inch photomultiplier. We began to calibrate every photomultiplier, calculate its position, how it was oriented after it reached depth, and calibrated every photomultiplier independently. And so we got a much better detector. But then the biggest news is, this was the time neural nets appeared and machine learning could go and look for these neutrinos instead of us. So when we did the analysis of the data, not using our intelligence, making cuts to get rid of the background, but let neural nets, taught neural nets, which are simulation, and then let neural net do it, then we got data samples that were much larger and better reconstructed. And that was the breakthrough. So we applied this not just to the future data, but we had kept every photon we had seen in the last 10 years, we had kept on tape and on disk. And so we had 10 years of better data. And so when we looked at the sky at 5 sigma, there this source emerged, which happened to be pointing at an active galaxy, which we should have anticipated from the fact we didn't see the galactic plane, but didn't. So it shouldn't have been a surprise. This galaxy is called NGC 1068, it was a surprise, actually. This was supposed to be, it was known to be an active galaxy, but not particularly suspected to be a cosmic accelerator. So here you see a picture of it, and you see the center of this galaxy showed this very strong emission in X-rays and in everything else. And so it's not just a galaxy where the black hole is active. That means, unlike our black hole, it's cannibalizing and eating, absorbing its own galaxy. That's what creates this hot core, because stuff is falling in. I'll go in a bit more detail later. But for the first time, we could show a picture where you see this is the number of events, neutrinos, and this is 1 degree from the source, 2 degrees, etc. And you see the red are the neutrinos produced by the atmosphere, and here you see an excess of 100 neutrinos coming from this galaxy. In this peak there are 100 neutrinos, and the observation is totally consistent with our simulation. Here you see the 10 years of data. There is the source, and within the 1 sigma error, you see that's the neutrino sky map. So in the last 3 years when we added data, it went from the publication of 80 neutrinos to 100 neutrinos, so it keeps growing. And when we first observed it and published it, it was we were 0.35 degrees of that source. Then, with the analysis with the improved detector, we were within 0.11 degree of the source. And in the last 3 years of data, we went into within 0.04 degrees of the source. So this source, the maximum likelihood tells you that the probability that this happened by accident in the sky map is like 1 in 400,000. So there's no doubt this is real. I sleep much better now. Here is the picture again. So it's an active galaxy with a hot core. That means it's emitting X-rays, actually, and it's surrounded by clouds of hydrogen. This is very important, and the astronomers tell us how much hydrogen there is and how much X-ray emission. And that we're going to put into trying to understand this source. Here is another picture. You see there is an accretion disk, so the matter is falling in, it's a spinning black hole. And you see here the accumulation of the radiation. And the radiation is X-rays. This core is so dense that gamma rays cannot get out. The first part, radiation that comes out is X-rays. And here you see another cartoon of this. So, this is a perfect picture of a cosmic accelerator to produce neutrinos. So you have the infall can accelerate particles. The magnetic fields in the accretion disk can accelerate particles. You have many ways to accelerate particles. but you're accelerating them in a region that's dense in material, and that's very important. And so, you see, Fermilab makes neutrinos by taking the accelerator beam, you shoot it in a target, and the target produces pions, and the charged pions decay into neutrinos and muons, and the neutral pions decay into gamma rays. And so, this is the NASA cartoon of this. You see somehow you accelerate protons, you pick up one of the X-rays, and by P-gamma interactions, you make charged pions that produce neutrinos and neutral that produce gamma rays. And so you can ask the question, where do I have exactly the right density of radiation and hydrogen so that I can produce my 100 neutrinos in 13 years? And I also have the density in X-rays to absorb the gamma rays from the pi zero that are not seen. And it has a unique answer. The density is at 10 Schwarzschild radii from the black hole. And so not only are they accelerated in active galaxies, they are accelerated right next on top of the black hole. And now I'm going to make a long story very short. Everybody by now had the idea, look at active galaxies, there are a lot of them, right? There are thousands of known galaxies, 10% are active, but look at the ones that have high X-ray fluxes. And that turns out to be very useful. We instantly started seeing other sources, not with all above the 3 sigma level, all taking all trials into account. So these are very, very likely detections. And the source that appeared everywhere is NGC 4151. And then for the experts, I show in green the other sources. We actually discovered one in the southern hemisphere, looking right in the flux of downgoing cosmic ray muons, Circinus. Everybody expected some other source, Sene. We don't see Sene, but Circinus stood out. And so by now, so who did discover these galaxies? These galaxies with a hot core were discovered by Carl Seifert in 1943. And he had a list just like us, and the top of his list in brightness was the same 2 galaxies, 1068 and 4151. So it's exactly a repeat what happened with light in 1943. In fact, now the best fit to our map, so we try to fit the sky map of 13 years of data, and so we ask the question, what's the hottest source? If you assume the sky is made by 2 sources, what's that probability? 3 sources, 4 sources. That's what's called a binomial analysis. The best fit to our present map is 17 sources. And you can look at them. That's our latest result. And what I'm not going to talk about is another thing we did very successfully, is when we now detect a neutrino, we started this in 2016. You detect the light, the computer at the South Pole reconstructs the direction of the neutrino. Typically, the data comes to Madison, Wisconsin. It's further analyzed and then sent out to the collaboration and eventually to the public. In the case of a very strong signal, we measure the direction approximately and immediately send in, every astronomer of the world has that direction of that neutrino within 30 seconds that the light goes through the ice. And we detected in 2017, using this method, With the cooperation of some 20 telescopes, we actually discovered a source, which we rediscovered now in our own data, TXS 0506, which was quite a surprise because the source is very far away, unlike the Seyfert galaxies, it's not very close. And so in this, what we call alerts, this source that you see at the bottom left, has already come up twice, which is very, very unlikely. And so this picture really begins to fit together. And so now it's time to stop. So if you think I'm going to say we have solved the cosmic ray problem, we have not. You know, I read the tea leaves with you, and so it's active galaxies somehow, but exactly which galaxies and what I think I can conclude is that, first of all, which wasn't clear when we started this adventure, neutrino astronomy exists. Even with a kilometer cube telescope, you can do it. The second thing we learned is that we need better telescopes, bigger, more neutrinos, thousands of neutrinos, not 100, with better reconstruction, better angular construction. And this is happening everywhere. The telescopes being built in the Mediterranean, in Lake Baikal, in the Pacific. There are 3 projects in China, one very ambitious, trying to anticipates building a 30-kilometer cube detector, and one of the coast of Canada, which I shouldn't forget. And so this is happening. You know, it's becoming astronomy with more telescopes and better telescopes. I think all I wanted to convey is that with neutrinos, you really have the technique to start identifying these sources and solve a problem that's more than 100 years old, right? It must be the oldest problem in astronomy. The one thing we have no clue and have not contributed to is we know that there are sources in our own galaxy that produce neutrinos. We know they're not very strong. We don't see the Milky Way. And so we actually have no idea right now what produces the high-energy cosmic rays in our own galaxy. That's a totally open problem. And it's interesting because this should be the easiest problem to solve. These sources are all nearby. And so it enforces this picture that's why we didn't see the galactic plane. And by the way, with machine learning thrown at our data, we did detect the Milky Way. You can see it here. You see the Milky Way at the South Pole, and in red, superimposed the neutrino signal. But the neutrino signal is like at a 10% level. You couldn't see it in the map I showed you, but it's there. And so I think the next frontier with this type of telescopes is go after sources in this picture and try to figure out what, for the experts, what makes the knee in the galactic cosmic ray spectrum. And I am out of time. I didn't do this alone, and I like to show my collaboration this way. These are the young people who did the work. Thank you.
Do we have any questions, particularly looking to the students to start this off?
Sorry. Yeah, thanks for that talk. You mentioned briefly, but what do you think the KM3-NET's high energy one? Because you haven't seen any high energy ones at that high energy, so what's good from there?
Well, they were lucky. You know, we have a couple events that are within 1 standard deviation, 2 standard deviations. And so there's nothing against being lucky. Of course, they were very lucky because we have a 10 times bigger detector that could see these events not for 13 years, but we analyzed our data while we were constructing the detector, and certainly would have seen, in fact, they saw it while they were constructing their detector. So and so the only way it can happen is that this is a source. It cannot be a steady flux. Either they were just lucky and picked up a fluctuation, and that extrapolates, will eventually align with the flux we measure. You cannot miss such an event. That's out of the question. But if the event was not just one event at one place, but also at one time, then it's not that inconsistent. And so maybe this event happened, will happen again in 10 years or happened 10 years ago. And when such an event has such high energy, it has a high neutrino cross-section, and if it's on the wrong side of the Earth, we don't see it. We would see it from the southern hemisphere easily, no problem. But the northern hemisphere, it doesn't make it through the Earth. So even when it's an episodic source, and it appears every 5 years or so, we could have missed it. But you can speculate as well as I can, right? And it's exciting. The other possibility is that when they get more events, they'll eventually align with us. And it's just, you have a small detector, and you only see the big events, and you're lucky to see one. Or there is something in the sky that we haven't noticed, and that's really exciting.
A very informed question. Let me pass on to Martin.
Thank you for that very nice talk. I hate to raise the spectre of statistics, but I'm sure I'm not the first person to have noticed that you seem to have detected about 30% of the small list of Seyfert galaxies that were discovered by Carl Seyfert. Seems to be quite a high percentage. He only found about 7 or 8, and you've got 3 of them.
Yeah.
You've got another 4 to go.
Active galaxies were part of the guess when I said theorists in their wisdom decided we needed at least a kilometer-cube detector. One of the objects we studied was how many neutrinos you get from active galaxies. But and it gave about this answer. But Seyfert certainly were not anticipated. The idea was that the neutrinos came from the jet of Sene, for instance. And, I mean, these Seyfert galaxies were uninteresting. It was really a failure of the theorist, including myself. I'm a theorist. That not to see this possibility that when you have this hot core where particles are accelerated, you produce neutrinos. And we were totally off in the wrong direction with jets. Jets don't produce neutrinos, and we understand why. The high energy photons come out, and there is no material to even when there are protons in the jet, there is no material to produce neutrinos. If you put enough material, you don't see the jet anymore. The high energy photons are absorbed. Nobody really anticipated. There were actually, I have to correct myself, just after the first ideas came around, in the early 1960s, there were Russian theorists that were on this track, but their work was forgotten. I wrote articles citing these people, but obviously I should have read the papers.
Yeah, as with all things, there's a Russian theorist got there first. Any more questions? I have one of my own, which I think I know the answer to. The maps you show of your sources are all in the northern hemisphere.
Yeah, of course.
Antarctica, if I remember my geography correctly, is at the very bottom of the southern hemisphere. Why is that?
No, this is because, you know, I emphasized how we discovered neutrinos using the electron neutrinos and tau neutrinos that interact in the detector. But to do astronomy, you have to go back to the original technique that I showed in the beginning, where you have this muon track that you can reconstruct at high energy to, we never really make it to 0.1 degree, but 0.2, 0.3 degrees. And those are the events you need to do astronomy. And then you look through the Earth, right? Looking through the Earth from the South Pole, you see the sky above Durham. And so you see the northern hemisphere. And it's very difficult. We now know how to look south, but we have 1/5 of the sensitivity. And we discovered this Circinus source, which is again, you know, like another galaxy of the same type.
So for all those people who think astronomy is just looking up, neutrino astronomy is looking down.
Yeah.
Constructively. Any more questions? Well, I think at that point, we should all thank Francis again for a very illuminating talk. And if anyone is interested in the Royal Astronomical Society, please come find me. Thank you.
Thanks for inviting me. It was a pleasure.